Hi, I'm Matt Tansik, and today I'll be presenting Block NeRF on behalf of my collaborators. The goal of Block NeRF is to extend neural radiance fields, also known as NeRFs, to arbitrarily large scenes. Once trained, these representations allow the user to visualize the scene from novel viewpoints that were unseen during training. For example, in this scene, the training images were captured from a vehicle traversing down this road. However, we can visualize the scene as if we're flying through it in a drone. In general, the data we use is captured from vehicles with cameras mounted pointing in all directions. These vehicles traverse the scenes on different days and at different times, leading to significant variation both in the vehicles in the scene and also in the lighting and weather. So we have to modify the NeRF networks to take into account this variation. Before we describe that, let's briefly recall how NeRF works. So NeRF shoots rays out into the scene and takes point samples along those rays. These point samples are then aggregated to predict the pixel color. Each of these point samples' position is going to be fed into an MLP to predict density. Density describes how much stuff there is in the scene. The point sample's direction is fed in later into the network to predict the color of that point sample. So in order to accommodate variations in color due to things like changes in weather and time of day, what we're going to do is condition that second MLP with an appearance embedding. This appearance embedding is unique for every training image and is optimized during the training procedure. So when you include these appearance embeddings, they help remove sort of ghosting artifacts that you get in NeRF, where you get this sort of fog. So we have rough camera poses for each of our training images. However, we find that if we further optimize the camera poses during training, we can get much sharper results. So for example, here, what you can see is on the left image, you get sort of a ghosting of these poles and objects in the scene, and generally blurrier results than when you include the pose optimization. Now, to handle dynamic objects in the scene, what we do is we use an off-the-shelf semantic segmentation algorithm to segment out those pixels, and we just avoid training on them. Now, finally, to scale to large scenes, what we're going to do is split up the scene into multiple NeRFs, which we're going to call block NeRFs. So in the case of a neighborhood, you might assign different block NeRFs to different intersections. And then for each of these block NeRFs, we're only going to train on images within a certain radius. Now, if we want to render a new image from this scene, the first thing we're going to do is we're going to filter out the block NeRFs that are a certain distance away. And this leaves us with a few remaining block NeRFs. And each of these remaining block NeRFs, we're going to render out their associated color and visibility. Visibility is another network output, which tries to predict whether or not a specific pixel is within the line of sight of the training images it was trained on. And so in this case, black means low visibility, which is what we see on the bottom NeRF. And so we're going to filter that out. And this leaves us with two images, which we're going to merge together using inverse distance weighting to produce our final render. Here is an example scene, test scene that we reconstruct. In this case, it's the Alamo Square neighborhood in San Francisco. And this was captured over a 3-month period, consists of 2.8 million images, 1,330 car rides, totaling 13.4 hours. If you were to just walk through all these streets by foot, it would take roughly 2 hours. And we're going to split the scene up into 35 block NeRFs. And one cool thing we can do is we can actually modify the appearance after the fact. And this allows us to transition from making it look like daytime to nighttime. And this is actually a very important property of our block NeRF, because we need some way to make sure that the appearance of neighboring blocks is consistent, so that when we travel through the scene, we're not constantly changing the appearance. And I'll finish this video off by just showing a few additional examples of reconstructions in downtown San Francisco. Thanks for watching.